glycogen to glucose?
Glycogen,
Glycogenolysis.
Glyco.
Glycogenolysis. What's the enzyme for glycogenolysis? Phosphorylase. Where does that occur? Going from glycogen to glucose. Can that happen in the muscle? Can you take the muscle glycogen and put it into the blood as glucose?
No. It's become the liver.
Once it's stored in the muscle as glycogen, it stays there until you turn it into G6P and take it through glycolysis. So where can we take stored glycogen and turn it into glucose in the blood?
Liver.
From the liver. So we take the stored glycogen in the liver, we turn it into glucose in the blood, and we bring it to the muscle to be metabolized that way. So liver glycogen is going to come into the muscle in the form of glucose. Good with that? Okay. What is the name for the process going from free fatty acids to triglycerides? Lipogenesis or esterification. Enzyme?
Ester enzymes.
Ester enzymes. Good. How about the process going from triglycerides to free fatty acid? Lipolysis. Enzyme? Lipoprotein lipase. Good. What's the name for the process where you go from amino acids to the liver to turn into glucose? Gluconeogenesis is the broad term. What's the more specific term? Glucosalanine cycle. What's the name of the process where you go from lactic acid to the liver to turn into glucose? Forward cycle more specifically, and a more broad term for that is gluconeogenesis. What's the enzyme for gluconeogenesis? Glucose 6-phosphatase. Good. Okay, everybody okay on that map and all the terminology? Okay.
That enzyme says the glucose 6-phosphatase. Is that also that's for the lactic acid part and the amino acid part? Where they both
Yes, that's the enzyme for gluconeogenesis in the liver. Yeah, so you're bringing amino acid to the liver to use that enzyme. You're bringing lactic acid to the liver to use that enzyme to turn it into glucose. Okay, then we talked about the ATP PCR system, which you use when? High intensity explosive exercise. How long can you stay in the system? 15 seconds. You have enough ATP stored in your muscle to last how long? About 3 seconds. And so how do you get to the 15 seconds?
Phosphorylation.
What's your substrate in this system? The PCR, the phosphocreatine. So the first 3 seconds you're breaking down your stored ATP. After that, you're breaking down your phosphocreatine using the energy that you got from breaking that bond to phosphorylize the ADP and create more ATP. Right? And then we had 4 more reactions we could do to kind of recycle in an effort to produce ATP very quickly. Right? Where does that occur?
In the muscle.
Where in the muscle? In the cytoplasm. Good. Aerobic or anaerobic?
Anaerobic.
Good. Okay, so then we said if you wanted to sprint for longer than 15 seconds, what do you have to do? Can you sprint for longer than 15 seconds?
Yeah.
Yes, you can. Can you stay in the system longer than 15 seconds? No. Okay, so if you want to sprint longer than 15 seconds, what do you have to do? You have to shift into the next system. Okay, so the next system we talked about was glycolysis. Where do we say glycolysis takes place? In the cytoplasm. Okay, what's the usable form of carbohydrate here?
G6P.
G6P, which stands for glucose 6-phosphate. Okay, that can come from either what or what? Glucose or glycogen. Okay, either way they're turned into glucose 6-phosphate. They go through a series of reactions and become what?
2
2 molecules of pyruvate. Okay, then that pyruvate is turned into
Lactic acid.
okay, so that's the process of glycolysis, and then we added the enzymes. What was the enzyme here?
Hexokinase.
What's the enzyme here?
Glucose 6-phosphatase.
What's the enzyme here?
Phosphofructokinase.
What's the enzyme here?
Lactate
Lactate dehydrogenase. Okay, this is as far as we got, right? Everybody okay so far? Okay, so it's a pretty simple process when you're going through glycolysis this way. Okay, it's pretty straightforward. So what we need to do next is count how many ATP will be produced. So if you take one molecule of carbohydrate and take it through the process of glycolysis, you're going to produce a specific number of ATP. Okay, so what you need to know during this process, remember I said there are a lot of reactions going on here, that right now you don't need to worry about those specific reactions. Just know that there are a lot of reactions going on here. So during those reactions, a bunch of different things are happening. Okay, there's an investment phase where you actually are going to consume an ATP. So during this process of glycolysis, at some point you're going to lose an ATP. Later on in the process, you're going to produce 4 more ATP. Okay, during those reactions that you're going through here. For this class, you don't need to know exactly where those occur, when those occur. In 446, you'll need to know a little bit more detail about when exactly those occur. Okay, so how many ATP will we end up with after that process of glycolysis? 3. So the process of glycolysis will yield a total of 3 ATP. Okay, that's if you're coming from glycogen. You come from glycogen, you go through the process of glycolysis, you'll end up with 3 ATP. Okay, so let's write down here glycolysis from glycogen will yield 3 ATP. Everybody okay with that number so far? Okay, so I'm specifying from glycogen because it's going to be a little bit different coming from glucose. Okay, where's the glucose? Is the glucose in the muscle? It's in the blood. Okay, so in order for the glucose to get into the muscle, G6P, it has to cross a membrane, because this is in the blood. Okay, in order to cross that membrane, it costs an ATP to get into the muscle. So if we come from glucose to G6P and go through the process of glycolysis, how many ATP will we end up with? 2, because we lost one coming into glucose. You don't lose that one coming from muscle glycogen because you're already in the muscle. You don't have to cross that membrane. Okay, so if we were to come from glucose, it would be 2 ATP. Okay, these are happening separately. I'm not going to add those together because I'm going to follow one molecule of carbohydrate through glycolysis. So if we have one molecule of glycogen going through glycolysis, how many ATP do we end up with? 3. If we have one molecule of glucose going through glycolysis, how many ATP will we end up with? 2. Okay. That's all you need to know as far as glycolysis. Questions on that? So, you're using this system. Is this aerobic or anaerobic? It's anaerobic. We haven't brought in oxygen in here anywhere. Okay? This is an anaerobic system without oxygen. So are you going to do this at high intensity or low intensity?
High intensity.
This is a system you use at high intensity. Remember, we're still sprinting. We started out in the blocks at the beginning of our sprint. Let's say we're doing a 400-meter sprint, 1 lap around the track. Okay, that's going to take a minute to a minute and a half, depending on how fast you're running. Okay, So for the first 15 seconds or so, we were primarily in the ATP PCR system using our stored ATP and recycling. After that, we shifted into our glycolysis, and we started producing ATP anaerobically that way. We can do this very quickly. Okay, so we're using this system at high intensity when we need to produce ATP very quickly. So we're not producing very much. Okay, 2 or 3 per molecule of carbohydrate is not very much, but we can do it quickly. So we can do it at high intensity. So we're still in our fast twitch fibers, mainly. Right? It's our fast twitch fibers that work glycolytically. So we're working at high intensity. Okay, so about how long do you think you can stay in this system?
A minute.
How long do you think you could sprint for? If I took you out to the track, started you on a start line, and said, okay, sprint as long as you can, how long do you think you could sprint for? 15 seconds? 30 seconds?
20 seconds.
Okay, so we already said we can sprint longer than 15 seconds, okay? It's challenging. Most of us aren't going to want to go much farther than that at our top speed. But remember that the 400-meter race is still considered a sprint, okay? How fast do elite sprinters do a 400-meter race?
40 seconds.
Under a minute,
48 seconds.
right? A sprinter will do a 400-meter race under a minute, okay? That's still anaerobic. It's still considered a sprint. Okay? Much longer than that is going to be difficult. Okay? What if I said, okay, you have to stand up and do squat jumps for as long as you can. Okay? Squat jumps, touch the floor, reach for the ceiling, touch the floor, reach for the ceiling. How long do you think you could go for?
A minute.
Do you think you could go for a minute? Let's try.
I'm not dressed for it right now.
So, by 20 seconds, a lot of you will be done. 30 seconds, some of you will still be going. By a minute, I don't think many of you will still be going. Okay? So high intensity, you can't do for very long, mainly because the lactic acid is building up, it's going to stop you. Okay? After the midterm, when we get into talking about fatigue, we'll talk about what is it exactly about the lactic acid that's causing fatigue. But you know when your legs start burning, you start getting out of breath, you don't have much longer to go at that intensity. Right? So what we say is generally, this system has a limit of about 2 minutes, okay? But 2 minutes in this system is extreme. A minute usually is pushing it, okay? But there's a range because there's a range of just barely getting into this system, at just barely hitting the high intensity, and then there's an extreme maximal intensity that you can't hold for more than 10 or 15 seconds. Okay, so there's a wide range there. So if you're at the bottom, just entering the system, it's actually possible to go longer than 2 minutes, which you'll see when you guys do 4:46 and you start training for the mile, doing the perfect mile, the fastest you can. You can actually do a mile and be highly anaerobic for a big chunk of it. Okay, but that's, you're at the lower end of the high intensity. If you're at the higher end of the high intensity, 15, 30 seconds, you're done. Okay, so there's a range there. But we're going to say generally the outer limit of the system is 2 minutes, and that's pretty extreme. Okay? If you want to run for longer than 2 minutes, what do you have to do? You have to slow down and shift into a different system. Okay? This is the end of our anaerobic systems. These are our 2 anaerobic systems, the ATP PCR system and glycolysis. So if we want to go longer than that, we have to decrease the intensity and shift into our shift into our aerobic systems. Okay, so remember when I drew that map of the substrates and the metabolic systems, I said you can use carbohydrate anaerobically through glycolysis. You can also use carbohydrate aerobically. And the way we do that is we start from glycolysis, but then we can continue metabolizing. Once we get to pyruvate, we can continue metabolizing this carbohydrate aerobically. Okay, so that's when it's going to become slow glycolysis. Okay, this glycolysis that we did here, you'll hear referred to as fast glycolysis. That's when you're working at high intensity, you're creating a lot of lactic acid, and you're only getting a few ATP. Okay, if you're doing slow glycolysis, it means you're continuing to metabolize the carbohydrate aerobically, and you're going to end up getting a lot more ATP from it. Okay, so you might want to label this one fast glycolysis, because we're going to redraw it as slow glycolysis on a different sheet of paper. It's going to start out like this, but then it's going to continue. And I want you to have a separate piece of paper so that we can separate the anaerobic from the aerobic. Okay, so label this one fast glycolysis, and then start a new sheet of paper for slow glycolysis. Okay, so we're going to start the same way. We have G6P. We can come from glucose. We can come from glycogen. We're going to go through a series of reactions and end up with 2-pyruvate. And this is all still happening in the cytoplasm. Well, this part is happening in the cytoplasm. Okay, as we go aerobic, we're going to shift into the mitochondria. Okay, so if we're working aerobically, when you're working aerobically, you're not producing as much lactic acid. So we're not going to go in this direction. We're instead going to go in this direction. Oh, I forgot to add the fates of lactate. Someone's going to have to remind me to go back and add that. Okay, so instead we'll go in this direction. This pyruvate will become acetyl-CoA. Stands for acetyl-coenzyme A, but you can just call it acetyl-CoA, that's fine. Acetyl-CoA is important because acetyl-CoA is your key to get into the Krebs cycle. Okay, you need acetyl-CoA to get into the Krebs cycle. One acetyl-CoA will take you through one Krebs cycle. So each pyruvate will give you an acetyl-CoA. So since we have 2 pyruvates, we have 2 acetyl-CoAs. That's going to take us through the Krebs cycle 2 times. Okay, once we get into this part, now we're in the mitochondria. Mitochondria is where all the aerobic metabolism happens. Okay, for glycolysis we were in the cytoplasm, and the glucose we were in the blood. Right? Questions so far? Yes?
We're in the mitochondria as soon as we start turning into the 2
The
acetyl-CoA.
acetyl-CoA, yeah. Should be in the mitochondria then. Going into the Krebs cycle. And that's where we're going to start consuming oxygen. Okay, the Krebs cycle and in the electron transport chain.
Can you go back in like slow glycolysis and fast glycolysis? Can you go back and forth?
Well, they're kind of both happening at the same time, which we're going to get into later after I've gone through each system. When one system is working, the other systems don't shut off. Okay? The systems are always all the systems are pretty much always working. It's just a matter of which one is your primary source of energy at any given time. So you're still going to be producing some lactic acid here, but we're primarily focusing here, so most of the pyruvate will be going in this direction. It doesn't mean that this is not happening. They're both happening. Good question. Okay, so the other important thing that's happening here is the electron transport chain. This is also in the mitochondria. So what's happening is, during this process of glycolysis, during these reactions, you're producing hydrogen. And that hydrogen goes along with electrons. Okay? So you'll have electron carriers. And their job is to pick up the electrons and take them to the electron transport chain. Okay? So in this case, my electron carrier is going to be NAD. You don't need to know what NAD stands for. We'll just call it NAD. Okay? That NAD is going to pick up the hydrogen with its electron. It's going to become NADH. Okay? You might see it written NADH like this. You might see it written NADH plus H plus. For me, you can write it either way. I will usually just be lazy and write it like this, which if you're a chemist is probably incorrect, but I'm okay with that. So I'll write it this. So it means the electron carrier, NAD, picked up the hydrogen with its electron, okay, and it's going to carry that to the electron transport chain. When it gets to the electron transport chain, it's going to hand off the hydrogen and the electron, and that hydrogen and electron is going to get passed down a chain in the electron transport chain. That process of passing the hydrogen and electron down the electron transport chain is going to produce energy. That energy is going to be used to phosphorylize the ATP. Do you remember what that means? Remember what it means to phosphorylate something? We had ADP. Phosphorylizing it means we added a phosphate. We needed energy to create ATP. Okay? So going down the electron transport chain, passing the hydrogen and the electron down the electron transport chain is producing energy. That energy is going to be used to phosphorylize this ATP. At the end of this chain, where you're passing down the hydrogen and the electron, there's oxygen at the end of this chain. Oxygen is the final acceptor of the hydrogen as you're passing the hydrogen down the chain. So when the hydrogen combines with the oxygen, you end up with water. So you're producing water at the end of this. Okay, and that's where you're consuming the oxygen. The oxygen is being consumed, turned into water. Okay, during that process, you're creating energy to make ATP. Okay. Now you guys were all frantically writing while I was doing that. Were you just drawing what I drew, or were you writing down what I said? You're writing down what I said? Some of you are writing down what I said, some of you are drawing what I drew? Okay. I'm going to go through it a couple more times. So if you drew it and didn't write, you can do the other. If you wrote it and didn't draw, you can do the other. Okay? And I'm going to go through it again after that. So don't worry, this is an important process. Okay. So during this process of glycolysis, you're producing hydrogen. You have an electron carrier. In this case, it's NAD. It's going to pick up the hydrogen. It's going to become NADH. It's going to bring that hydrogen with its electron to the electron transport chain in the mitochondria. Okay? That hydrogen electron is going to be passed down a chain. As it gets passed down the chain, it's producing energy. That energy is going to be used to build ATP, phosphorylation. Okay? The end of this chain, there's oxygen waiting there, hopefully. So when that hydrogen gets to the end of the chain, meets the oxygen, it's going to consume the oxygen, turn it into water. Okay, so because, okay, we already said this process is called phosphorylation. Just like it was during the ATP PCR system. Okay, but in this case, this energy is being produced oxidatively. Right? We had to consume oxygen in order to produce this energy. So this process becomes oxidative phosphorylation. Because the energy came from consuming oxygen. So that process, the ADP plus inorganic phosphate plus energy producing ATP, that process is phosphorylation. If the energy came from consuming oxygen, then you would call it specifically oxidative phosphorylation. In the ATP PCR system, it wasn't oxidative. The energy was being produced just from breaking the bond of the PCR, right? So that was just phosphorylation. This is the same process, using the energy to create ATP, but because this energy came from the consumption of oxygen, we now call it oxidative phosphorylation. Okay, so sometimes phosphorylation is oxidative, sometimes it's not. Questions so far? Yes.
Can you go over the part when we're producing water again?
Well, you're passing hydrogen down this chain, and there's oxygen waiting at the end of the chain. Okay, so when you get the hydrogen and the oxygen together at the end, they combine to produce water.
Okay. So it's more. There's more than just like one oxygen. There's like several oxygen.
Yeah, yeah. Hopefully, there's a lot of oxygen.
Right.
Okay. Anybody have a water bottle? Okay. I'm going to do an experiment. I've never done it this way, but I've been thinking about doing it for a couple of semesters, so I want to try it this semester. You guys are making it. I need give me 5 volunteers to come up here and be my electron transport chain, and we need a water bottle. I'll take your water bottle. Okay, so just line up here facing the class.
I'm gonna answer questions.
No. You're just going to be passing the water. Okay, move this way. Move this way.
Redox reaction.
Okay, so I'm in glycolysis. Okay, this water bottle is the hydrogen and the electron. Okay, so you guys are the electron transport chain in the mitochondria. Each of you is called a cytochrome. Okay, the electron transport chain is made up of cytochromes. Yes, so this is glycolysis producing this hydrogen and electron. I'm the NAD, I'm the electron carrier. I'm going to grab the hydrogen and the electron, I'm going to carry it over to the mitochondria. Okay, anytime somebody is holding the hydrogen, they are considered reduced. Okay, if you're holding the hydrogen, you're considered reduced. If you give up the hydrogen and the electron, you're considered oxidized. Okay, so right now, I'm NADH. Am I oxidized or reduced? Reduced because I'm holding the hydrogen. Okay, I'm going to pass it off to the first cytochrome in the electron transport chain. Now am I oxidized or reduced? I'm oxidized, and what is he? Okay, he's going to pass the hydrogen on. Now is he oxidized? This one, oxidized or reduced? And what is he? Okay, he's going to pass it down. Okay, now this one is oxidized, this one is reduced. In between them, they produced energy that created an ATP. Okay, he's going to pass that down. He is now oxidized, he is reduced. They produced another energy here, produced another ATP. Okay, he passes it down. What is he? What is she? Reduced. They produced another energy for another ATP. Okay, at the end of the chain, I'm going to play another role of oxygen. Okay, I'm going to grab the hydrogen, I'm going to become water. Okay, so in the process of this electron transport chain, you're passing down the hydrogen and the electron stay together. You're passing it down a chain of cytochromes. As you pass it down the chain of cytochromes, you're producing energy. Okay, so here we produced 3 energies. Okay, I said that 3 times. Each energy, theoretically, is enough to produce 1 ATP.
4, right? 4 of us. Say in between 1.
I didn't say it in between here.
Oh,
Did I?
so not-
I said it in between here, I said it in between here, and I said it in between here.
There we go. Yeah, here.
Positive.
1 hydrogen and electron going through electron transport chain once is actually going to produce, on average, 3 of those. Okay, I'm going to talk about that again in a minute. Okay, so 1 hydrogen electron is going to go through the electron transport chain. These are called redox reactions, okay, because it was oxidation, reduction, oxidation, reduction, oxidation, reduction. So we call them redox reactions. Okay, that's the passing of the hydrogen and electron down the chain of cytochromes, producing energy for the purpose of oxidative phosphorylation. Okay, let me say that sentence again. Okay, This process in the electron transport chain is called redox reactions. Oxidation reduction as you're passing the hydrogen and the electron down the chain of cytochromes for the purpose of producing energy for oxidative phosphorylation, which means we're producing ATP. We good? Okay. Thank you, guys. Have a seat. Okay. So if I were to draw that here, if this is the electron transport chain, these are my cytochromes. Okay, and I've got oxygen here waiting at the end. My NAD is going to bring the hydrogen and the electron here, pass it off. It's going to reduce this. When it hands off the hydrogen here, this will be reduced. This cytochrome will be reduced. Okay, when this passes the hydrogen here, this will be oxidized, this will be reduced. It's going to pass it here. This will be oxidized, this will be reduced. Yes, this is going to create energy. It's going to pass it here, oxidation, reduction, energy, oxidation, reduction, energy, and this is going to produce water. So the whole point of this is to produce energy for oxidative phosphorylation, to produce ATP. So each time we go through glycolysis, this happens twice. Yes.
I got lost. So, is the H2O happening after that, after the electron transport chain, or is it happening after ATP plus PI?
The oxygen? The oxygen is the final acceptor at the end of the electron transport chain.
So then H2O happens.
So while we're going through this chain, we're creating ATP, the end of the chain, we're creating water.
And then what happens right here with ATP? Oh, got it. Got it.
Yes?
What was the process? Again,
These are redox reactions, which stands for reduction and oxidation. Okay, and just a little mnemonic to help you remember. Oil rig. Oxidation is losing an electron. Reduction is gaining an electron. So that helps you remember when you're oxidized and when you're reduced. You're oxidized when you have lost the electron. You're reduced when you have gained the electron. Okay, so what is NAD? A hydrogen transporter, or I'll refer to it as an electron carrier. Either way, it's I would accept. Okay, so NAD is an electron carrier. It carries the electron to the electron transport chain in the mitochondria. Okay, what is NAD?
carrier
Where does it go?
to the
Electron transport chain.
In the,
mitochondria.
okay, I need everybody to say this with me together. This is going to help you remember it. What is NAD?
Electron carrier
An electron carrier. Where does it go?
to the electron transport chain.
In the,
Mitochondria.
okay, that was about 50%. Let's see if we can get 80%. What is NAD? Where does it go? In the, good. What's happening in the electron transport chain? Redox reactions. Oxidation, reduction, passing the hydrogen and the electron down the chain of cytochromes. producing energy for oxidative phosphorylation to create ATP. Consuming oxygen in the process. Yes?
So it produces 3 ATP and 1 water molecule.
Okay, so here's the deal. When we draw this, theoretically we're producing from one hydrogen coming through, one hydrogen and one electron coming through, we're creating 3 ATP. But there are other processes going on that are going to consume ATP as you're transporting things around here. So when you get into 446, it's not going to actually be 3 ATP from one NAD, it's going to be 2.5. You can't produce a half an ATP. You're only producing whole ATPs, but it's an average based on all the anabolic and catabolic processes that are going on. So I'm going to say for each NAD that takes a hydrogen to the electron transport chain, you're going to yield 2.5 ATP. Okay? And that way, those of you who are going into 446 don't have to relearn the numbers. So if I teach it to you as 3, when you get into 446, you're going to have to change all your numbers around. Okay, so I'm just going to leave it as 2.5, and that way it'll be a smooth transition to 446. Okay, so each NAD that takes you through the electron transport chain is going to give you 2.5 ATP. During this process of glycolysis, that happens twice. So how many ATP do we just gain from the electron transport chain?
5.
Okay, so we gain 5 ATP. Going through this process of glycolysis, we still have the original -1 and the original +4. That's going to happen every time you go through glycolysis. Do you remember those? So if we came from glycogen, going through slow glycolysis, which means we have time to go through the electron transport chain, how many ATP do we have so far?
The end after everything.
So far, what we've done.
5 ATP.
If we came from glycogen, and we've gone this far so far, we have 3 here, and we have 5 here. So far we're at 8. Everybody see that? Okay, but we're not done, because we're going to continue going through this way. Okay? In between pyruvate and acetyl-CoA, you're going to get another 2 NADs. What is NAD? Okay, I need more people responding. What is NAD? Where does it go? In the, okay, and we understand what it's doing there, right? It's going to pick up the hydrogen, take it here, you're going to go through the electron transport chain. How many ATP per NAD?
2.5.
Okay, so I'm going to say times 2.5 ATP each is going to give me how many ATP here?
5.
5 more ATP. Okay, now we're at acetyl-CoA, and we're going to go through the Krebs cycle. In the Krebs cycle, was there a question before I do the Krebs cycle? Okay, in the Krebs cycle, we have another 3 NADs. What is NAD? Where does it go? In the, okay, so I'm going to draw a line here. How many ATP is that going to give me? 2.5 ATP each, which is going to give me 7.5 ATP from this. Okay, we're also, during the Krebs cycle, we're going to have an FAD. An FAD is also an electron carrier. It's going to do the exact same thing as NAD. It's going to pick up a hydrogen. Okay, because in this process you're also producing hydrogen. It's going to pick up the hydrogen. It's going to take it to the electron transport chain, go through the redox reactions, and produce ATP. But the difference is when you have an FAD, hydrogen, it joins the process, it joins the chain later. It's going to join the chain here. Which means it's not going to produce as much ATP because it skipped over this first one. And it joined this cytochrome chain after this first ATP would normally be produced. So the FAD is going to produce less ATP than the NAD. It's entering the chain later. Okay, you'll get more detail about that in 446. So that means, if you look at this, the FAD is coming in here, and it's going to create 2 more energies after that, 2 more ATPs. But because of all the metabolic processes happening, we're going to say that each FAD is going to give you 1.5 ATP each. And we just have 1 right there in the Krebs cycle. So I'm going to say plus 1 ATP.
1.5.
Thank you. 1.5 ATP. Okay, there's also another ATP just spontaneously produced here during the Krebs cycle. Kind of like these were produced here during glycolysis. Not from the electron transport chain, just spontaneously produced here. There's another ATP spontaneously produced here in the Krebs cycle.
And it would be just one FAD, right? Just one FAD.
Yeah, 1 FAD. So you have 3 NADs, 1 FAD, and 1 direct ATP, which I'll talk about again in a minute. Okay, so each Krebs cycle is the same. How many total ATP did I get from this Krebs cycle? 7.5, 1.5, and 1. Does everybody see how that's 10 ATP? Oops, 10 ATP in that Krebs cycle. Yes? Okay, so each Krebs cycle is exactly the same. So I'm going to have another 3 NAD, another 1 FAD, and another direct ATP. Each NAD is going to give me 2.5 ATP each for a total of 7.5. This is going to give me 1.5 ATP from the electron transport chain, so this is plus 1.5, and this is plus 1. So I have another 10 ATP from this Krebs cycle. So, if I came from glycogen, how many total ATP did I produce? If I came from glycogen, I have these, which is 3. I have these 5, we're at 8. I have these 5, we're at 13. 23, 33. So 1 molecule of glycogen going through slow glycolysis, which is going to include the aerobic side, is going to yield 33 ATP. Significantly more than if we just went through anaerobically, right? Anaerobically, we only got 3 ATP. Continuing to metabolize aerobically, we got 33. Okay, so you can get a lot more ATP aerobically, but it takes longer and it takes oxygen. So that's why you can only do it at the lower intensities. If we came from glucose, how many total ATP would we have? 32. How do we know that? We didn't have to recount the whole thing. What did you do differently? If you come from glucose, you lose an ATP crossing into the muscle. So if you come from glycogen, you're going to end up with 33 ATP. If you come from glucose, you're going to end up with 32 ATP in slow glycolysis. questions so far?
You said, for the glycogen it's 32?
Glycogen is 33,
33.
glucose is 32. So those are numbers you should just know. Like if I were to ask you how many molecules of ATP are produced from the metabolism, the aerobic metabolism of one molecule of glycogen, you should be able to say 33 like that without even thinking about it. That's a number you should know. And if I say glucose, it's 32. It's a number you should just know. Okay? But you'll need to be able to show me exactly where they're coming from. Okay? So if I were just to say how many ATPs are produced from the aerobic metabolism, or I might say, I'm more likely to say the complete oxidation. Okay, if I use the word oxidation, what does that mean?
Slow.
You're using oxygen, so you know it involves all of that. Okay, so if I say how many ATP are produced from the complete oxidation of one molecule of glycogen, and then I put a little line, you're just putting the number. That's a 1-point question. Okay? I have to tell you, I'm more likely to give you a whole page of paper and say, how many, ask the same question, but then I say, show me where they all come from. And then you giving me the 33 is 1 point out of the 20 that are possible from drawing this whole thing out. Okay, so you need to be able to draw this whole thing out, show me exactly where they come from.
When we have to draw the Krebs cycle, do we have to like put like how to add them to 10, or can we just put 10?
No, you have to put the details. Okay. Yes. And so notice how I wrote times 2.5 ATP times 2.5 ATP. I wrote that out every time. I'm not just putting 3 NAD, 7.5. I'm putting how I got the 7.5 because each ATP was 2.5. Okay? I took the time to write that out every time because I want you to take the time to write it out every time. I want to know that you understand exactly where each ATP is coming from. I don't want to know that you're just memorizing those numbers. I want you to be able to explain to me why. Why are you getting 2.5 ATP from each NAD? Well, because it's going through the electron transport chain and it's producing this much energy. Each time you produce an energy, you go through oxidative phosphorylation and creates an ATP. Okay, so this is a big, complex, integrated process. Yes?
Does this also happen to lactic acid? Or?
No, lactic acid is if pyruvate goes in the other direction.
But isn't that how much? So how do we do the 32 ATP?
If you're coming from glucose, going through glycolysis, and then going this way.
Oh, okay.
Okay, so I'm not saying if you come from glucose, you're going in this direction. If you come from glycogen, you're going in this direction. That's not what I'm saying. Okay, you can come from either direction. Once you get to G6P, this is the same. Okay, it might get a little confusing looking at the diagram in the book because the diagram in the book does do it that way. It does this side for this and this side for that, and so it's repeating things on each side, and I think that gets really confusing. So the image in the book might confuse you. I prefer you to look at it this way. Okay, the process from G6P to pyruvate is exactly the same whether you come from glucose or glycogen. So it doesn't really matter. I could write these on this side of the line. It doesn't really matter. Yes.
So the redox reduction is happening in the Krebs cycle, right?
Yes, the redox reactions. No, the redox reactions are the electron transport chain.
So I got kind of confused of where after the says 3 NAD, how do you get 3 NAD? Yeah.
Well, there's hydrogen being produced here. So there are electron carriers here that are going to take the hydrogen up to the electron transport chain. So there's a series of reactions happening through the cycle. And again, those of you going to 446, you're going to have to memorize every single reaction happening in this Krebs cycle. Okay, for me right now, all you need to know is your electron carriers, where the ATP is produced. I'm going to give you enzymes in a minute. Let me answer other questions first. Yes?
So once it reaches up there to like electron transport chain, that picture from right there, is that what's happening, right?
Yes, this
Okay.
is the magnification of the electron transport chain.
So all that stuff is going there and going through that process, the redox.
Yes.
Did you want us to add that picture as well as that picture? Or it's just that something to refer to?
Yeah, this is more something to refer to. This is the drawing I'll be looking for when you're accounting for ATP. I would usually keep the electron transport chain as a separate question, but I could ask you to explain the electron transport chain as well. In which case, you could explain it in words, you could explain it with a drawing, you could explain it with people up in front of the clock. What else is bothering you? Okay, so we have a couple different kinds of ATP happening here. We have some ATP that's just produced kind of spontaneously during these reactions where they're happening, and then the rest of the ATP is being produced in the electron transport chain. Okay, so we have different terminology for those. Any ATP that come from the electron transport chain are considered indirect ATP. Any ATP that come from the electron transport chain are considered indirect ATP. So the ATP that are not coming through the electron transport chain, which would be these three, this one, and this one, are considered direct ATP. Okay, so if I were to ask you how many direct ATP are produced from the complete oxidation of one molecule of glucose. Let me ask you that again. How many direct ATP are produced from the complete oxidation of one molecule of glucose? What's your answer?
4.
Coming from glucose. How many am I getting here?
2.
2. Because I lost one here. Lost one here, made 4. So I have 2. These are all indirect. 3, 4. All the others are indirect. Okay, if I asked how many direct ATP are produced from the complete oxidation of one molecule of glycogen, coming from here through here, we have 3, 4, 5. Coming from glycogen, 3, 4, 5. If I were to ask you how many indirect ATP are produced from the complete oxidation of one molecule of glucose, could you figure that out? 5, 5, 9, 9. Right? Everybody follow that? Because of the 10 ATP in Krebs, 9 of them are indirect and 1 of them is direct. 9 of them are indirect and 1 of them is direct. How many total ATP from the complete oxidation of one molecule of glucose? 32. That should fall right off your tongue. Okay, so you need to be able to answer questions like that. The way you're going to be able to answer questions like that is being able to draw this out. Okay, but when you draw this out, you have to also show me how it adds up. So what you can't do is draw all this and then say, my answer is 33. You have to show me how that adds up. Okay, so you could do something like show me the 3 plus the 5 plus the 5 plus the 10 plus the 10 would add up to 33. So I can see where you're getting the 33 from, and I can see where all these numbers are from. Okay, you can do something like that. There's also a table you can draw, which is in your slides and in your book, where you say the process of glycolysis. You make a table out of it. Okay, and you say direct ATP, indirect ATP. Okay, so the process of glycolysis, if we're coming, let's say we're coming from glycogen. Okay, so we'll label this from glycogen. Going through glycolysis, where does glycolysis end?
At 100.
Where does glycolysis begin? Glycolysis begins at G6P. Where does glycolysis end? Pyruvate is the end product of glycolysis. Okay, so from glycogen through glycolysis, how many direct ATP do we have? 3. How many indirect?
How is it just 3 direct?
Minus 1 plus 4. Okay, we have the Krebs cycles over here. Going from, bless you, going from pyruvate to acetyl-CoA, is that part of glycolysis? No. Is it part of the Krebs cycle? It's not. Krebs cycle is in here. So we call this the intermediate step because it's in between glycolysis and Krebs. Okay, so the intermediate step, which is from pyruvate to acetyl-CoA, how many direct ATP are produced in the intermediate step? Are those 5 direct or indirect? How do you know they're indirect? They're from the electron transport chain. Any ATP that are produced in the electron transport chain are indirect. So those 5 are indirect. How many direct are we getting there? None. We have 2 Krebs cycles. I like to keep them separate because we'll need them separate later. Okay, so in one Krebs cycle, how many direct? How many indirect? 9. Second Krebs cycle is the same. How many total indirect? How many total direct? 5, and that should add up to 33 total. Okay, so if you do it this way, if I ask you how many direct, you have a number. If I ask you how many indirect, you have a number. If I ask you how many total, you have a number. I might ask for all 3. You need to be ready. Yes? Intermediate step is from pyruvate to acetyl-CoA. Because you're in between glycolysis and Krebs. So if I were to do this from glucose, what would be different? This would be a 2. So this would be a 4. So this would be a 32. Okay. I'm going to add enzymes to this process, and then we'll be done with this process. Okay, here we already know the enzyme. What is it? Here we already know the enzyme. What is it?
Glucose 6-phosphate.
Glycolysis, we already know the enzyme. What is it?
Phosphofructokinase.
Okay, from pyruvate to acetyl-CoA. Now LDH goes to lactic acid. Going to acetyl-CoA, we're going to have pyruvate dehydrogenase. What was the rate limiting enzyme of glycolysis? Okay, in Krebs, I'm going to give you 3 enzymes. I'm going to write them in kind of specific areas because those of you going into 446, you're going to have to memorize all these different reactions and you're going to need to know where those enzymes are. So you might want to write them in the general area. Those of you who are not going into 446, you can just list the 3 enzymes. I don't really care where on the circle they are. If you put them in a different part of the circle than I put them in, I'm not going to mark you off for that. Okay, I'm just going to put them in the correct general area, so those of you going into 446 will have an idea of where they go. Okay, so going around in this direction, we're going to have IDH, which stands for isocitrate dehydrogenase. Down here we're going to have SDH, which stands for succinate dehydrogenase. And over here, we're gonna have CS, which stands for citrate synthase. So notice there's citrate in two of these. They used to call the Krebs cycle the citric acid cycle. So that might help you remember the isocitrate and the citrate synthase. The IDH, the isocitrate dehydrogenase, is the rate limiting enzyme for the Krebs cycle. What does that mean?
Controls the rate.
It controls the rate. So if you activate IDH, Krebs cycle goes faster. If you inhibit IDH, Krebs cycle goes more slowly.
Is it in that order? Or
Is what in order?
IDH, SDH?
Yes. In Krebs cycle, you encounter the enzymes in this order. But for this class, I don't need them to be in order. If you put them in a different order, I won't mark you wrong. But if you're going to 46, you're going to need to know them in order, and there will be other enzymes in there as well. I'm only giving you 3. Okay, giving you one enzyme for the electron transport chain. That is
Cytochrome oxidase.
Oxidase. That is a rate limiting enzyme for the electron transport chain. Okay. Questions on this? I need to move on because I have to finish chapter 2 and do chapter 4 on Tuesday. And then your review is Thursday. And then your exam is the following Tuesday, is that right?
March 1st. March 1st.
Okay. So right now is the 18th. So we have Tuesday we're finishing lecture, Thursday we're reviewing, Tuesday midterm. So we gotta finish up. So questions on this? Yes?
We're going to talk about the fates of lactate.
I'm gonna do that on Tuesday, okay? Because I want that on the fast glycolysis one. I don't wanna go back to that right now because I need to do fat. Okay, so we're working aerobically. Remember that we're working aerobically, we have Krebs cycle, electron transport chain, and what's the other process we haven't done yet? Think about the big map we drew and we listed all the different metabolic systems. We haven't done fat yet, right? What's the system called where we use the free fatty acids?
Beta oxidation.
Beta oxidation. So we've got to do that one real quick. Okay, so I'm going to erase this. Okay? I'll draw it again, I promise. And also, if you're confused, you can stay for the 11 o'clock. I'm going to do it again. Okay, so when we're talking about fat, now we need a new piece of paper. We're getting into beta oxidation. Okay, the free fatty acids are going to come in long chains of carbons. You guys are going to have to tell me when we're out of time. So let's say we have a free fatty acid that has a chain of 14 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so if we're going to go through beta oxidation, the first thing that has to happen is we have to activate this free fatty acid. Okay, the free fatty acid is basically a glycerol with 3 fatty acids attached to it, so we kind of have to separate the glycerol from the fatty acid, and that's activating it so it can go through beta oxidation. Okay, so that process actually costs, did we do 1 ATP or 2 ATP last semester?
You did 2 last semester.
I did 2 last semester, and Kelia, you're saying I did 1 2 semesters ago?
446, Dr. Loy uses 1.
Dr. Lewis is 1? Okay. We'll use 1. Costs an ATP We've done it with 2. We did it with 2, right, Kelia?
Yeah, last semester.
But Dr. Lloyd does 1.
Yes.
So I hate for them to have to switch. I'm gonna get confused if I switch. Okay. We'll say it costs 1 ATP because I want to be consistent with Dr. Lloyd. What does Dr. Haneke do?
I'm not. I think she does 2.
Lovely.
You blow it.
Okay, I'm going to attempt to stick with Dr. Lloyd. Okay, so costs 1 ATP to activate the free fatty acid. The process of beta oxidation means you're separating a pair of carbons from the chain. The process of beta oxidation means you're separating a pair of carbons from the chain. Each time you go through beta oxidation, you separate a pair of carbons from the chain. That will give you 1 NAD and 1 FAD. What are those?
Electron transport.
Where do they go? In the mitochondria. Okay. Each NAD is going to give me how many ATP? Each FAD is going to give me how many ATP? So I'm going to have a total of 4 ATP from this process. Would you agree? Okay. So this chain is going to go through beta oxidation again. Beta oxidation means you're separating a pair of carbons from the chain, gives you an NAD and an FAD. They go through the electron transport chain, and end up with 4 ATP. Okay, I'm going to write that here. I'm going to say each pass through beta oxidation yields 1 NAD and 1 FAD that go through the electron transport chain. Okay, that's going to explain where this 4 is coming from. Okay, I'm going to go through beta oxidation again. 4, beta oxidation, 4, beta oxidation, 4, beta oxidation, 4. Does this pair of carbons need to go through beta oxidation? What does beta oxidation mean? Separating a pair of carbons from the chain. By the time we get here, we've just got 1 pair of carbons left. Is there a chain to separate it from? No. There's not. So this pair of carbons does not go through beta oxidation. If it does not go through beta oxidation, it does not give you these electron carriers. You do not get these 4 ATP. Does everybody understand why I'm not putting a 4 there?
Say it again.
Each time you go through beta oxidation, you're separating a pair of carbons from the chain that gives you these electron carriers, that gives you these 4 ATP. By the time we get to the end of the chain, there's only 1 pair of carbons left. We don't need to go through beta oxidation because there's no chain to separate this from. And it was the beta oxidation that gave us those electron carriers, so we don't get them. Okay. After that process, each pair of carbons is going to give you an acetyl-CoA. What does acetyl-CoA do for you? It takes you to the Krebs cycle. So this acetyl-CoA is going to take us through the Krebs cycle. What do we know is happening in the Krebs cycle? What do we have up here? 3 NADs, 1 FAD, and 1 ATP. How many total ATP from this Krebs? 10 total. How many of them are direct?
Direct?
How many of them are direct? 1 direct, 9 indirect. Right? Are these 4s, are they direct or indirect? How do you know they're indirect? They're coming from the electron transport chain, so they're indirect. I'm going to keep the direct and indirect separate because I'm going to be asking you for a count of indirect and direct. You need to keep them separate. Okay? So I'm gonna put, since these are indirect, I'm gonna put the indirect ones from here with it. So I'm gonna put 9 and 1. Because these are indirect and these are direct. Everybody okay with that? So each pair of carbons is gonna give me an acetyl-CoA that's gonna go through Krebs. It's gonna give me 9 and 1. 9 and 1, 9 and 1, 9 and 1, 9 and 1. Do we get those? Sorry. Do we get these 10 ATP for this pair? Why not? What gave us the acetyl-CoA?
Okay.
Each pair of carbons. Each pair of carbons gives you an acetyl-CoA. Is this a pair of carbons?
Yes.
Yes, it gives you an acetyl-CoA. It doesn't matter that this pair of carbons didn't go through beta oxidation. Okay, we didn't get these electron carriers because we didn't go through beta oxidation. But it's still a pair of carbons, so it's still going to give us an acetyl-CoA. It's still going to go through the Krebs cycle, give us 9 and 1. Okay, so these are indirect, these are indirect, these are direct. Let's count them up. 1, 2, 3, 4, 5, 6 times 4 is 24. 7 times 9
63.
63. So total indirect, 87. Yes, check my math, please. Direct, we have 1, 2, 3, 4, 5, 6, 7. What haven't we accounted for yet? The one we lost here to activate. Okay? The one you lose is considered direct. So you have to subtract that from the direct before you add these together. Because if you add these together and then subtract, it's going to mess up your direct and indirect ratio. Because you'll end up taking it from indirect. So we got to subtract 1 for the activation. We're going to end up with 6. Okay, so what's the total?
93.
87 plus 6. What is it? 93.
3.
Does everybody agree?
Yes.
Okay, so if I were to ask you how many ATP are produced from a 14 carbon chain fatty acid, you should be able to count them up and tell me a total. You should be able to tell me how many direct and how many indirect and show me where they're coming from. Okay, you also need to explain the process. I'm almost done. Beta oxidation is separating a pair of carbons from the chain. Each pass through beta oxidation yields 1 NAD and 1 FAD for the electron transport chain. That explains the 4. Then you need to say each pair of carbons yields acetyl-CoA, which goes through Krebs cycle. Okay, and that explains where the rest of these numbers are coming from. If I ask you to explain to me where the ATP is coming from in a free fatty acid, if you just do this chart with the numbers, you're not going to get full credit. You can't explain the process of getting ATP from fatty acid without explaining the process of beta oxidation. Okay, so you've got to name the process, you've got to explain what it is, and then you've got to explain where these numbers are coming from. So you've got to do this whole thing, including the explanation paragraph. Yes?
So the 9 and the 1s are I'm sorry, the 4 and the 9s are indirect?
Yes.
And 1 is direct?
Correct.
Okay.
So what you should practice doing, I don't have time to do it in class right now, but what you should practice doing, the chains are not always 14 carbons long. Sometimes they're 16, sometimes they're 18. So how is this going to be different if the chain has 16 carbons in it? Yeah, you're going to get more ATP. So the longer the chain of carbons is, the more ATP you get from it. So you should practice doing this with a 16 carbon chain, okay, which we'll do on Tuesday before we get into chapter 4. Chapter 4 is going to be quick.
One acetyl-CoA gives 1 Krebs cycle?
1 acetyl-CoA gives 1 Krebs cycle. Yes. Okay, real quick, you guys, grab your phone. I want you to do a real quick quiz if you can before you leave. If you have to leave, that's fine, but if you could do this, give me an idea of where you stand, I would appreciate it.
That's Heavy, huh?
So log into Fleck S16. And there's a quiz there for you with a few questions. Just see how you do. I don't expect you to know this stuff really well yet, okay? We just covered it. But I just want to see where you stand with it, and we'll go over it again. This is one side direct. This is one direct, comma, 9 indirect. Looks like we need to study the enzymes a little bit. That's okay. Alright, you guys, I will review this stuff quickly on Tuesday, because then I need to finish chapter 4 as well. So please, please, please go to office hours. Have a good weekend.